Hello everyone and Pa Reza. My name is Daniel Winston Mandela Tulung and my teammates are Adam Maulana Haq and Rindra Adriansyah, and here in this video we will try to understand computational complexity through simplified concept of P, NP, NP hard, and NP complete. Alright, let's get right into it. So first of all, what is polynomial time? If we were to go to its definitions, these are problems that can be solved efficiently in polynomial time basically, meaning that the time it takes to solve the problem grows at a manageable rate as the problem size increases. Now, there are several, or actually just two key points in polynomial time, and these are one, the problem needs to be solvable in a reasonable amount of time, and two, the algorithm has a clear logical process and it has to be deterministic. These are the key points that we need to look forward to classify and understand whether a certain problem is polynomial or not. Now, some examples of polynomial time are when we sort numbers, when we find a shortest path, or when we do matrix multiplication. Now, let's delve into these examples and find out why these are polynomial time further. All right, so let's see here first. Now, why is sorting numbers, such as merge sort and quicksort, considered polynomial time? Well, first, let's look at the definition of P again. The class P consists of problems that can be solved in polynomial time, meaning that the time taken to solve the problem can be expressed as big O n to the power of k, where n is the size of the input and k is a constant. Now, these problems are efficiently solvable by a deterministic Turing machine. Now, let's say, for example, we delve more into merge sort. Now, merge sort works by recursively dividing the array into halves until each subarray has one element, then merges the subarrays in sorted order. Now, the time complexity to merge sort is O n log n, where n is the number of elements, and n log n is polynomial time complexity because log n grows slower than any polynomial n to the power of k for k bigger than 0. Now, if we were to look at quicksort, quicksort basically selects a pivot, partitions the array around the pivot, and recursively sorts the partitions as we can see in this illustration here. Now, the average case time complexity for quicksort is same again as merge sort, O n log n, and the worst case time complexity is O n to the power of 2 here. Now, this is if the pivot is poorly chosen, but this is still polynomial. Now, again, I guess to wrap up, if you were to look at the correlation between these sorting algorithms, merge sort and quicksort, the reason why, another key reason why they are polynomial is because of their deterministic nature. These sorting algorithms like merge sort and quicksort follow deterministic rules for splitting, comparing, and combining elements. They do not rely on any guessing or non-deterministic steps. Sorry, they're an algorithm, meaning that after every step, there is code or pseudocode or basically an instruction to tell it what it should do next. There's no guessing. It is all deterministic, hence why it is considered polynomial time. Now, let's go ahead and look at why Dijkstra's algorithm is considered polynomial time. So again, a little overview on Dijkstra's algorithm is that it is basically an algorithm to find a shortest path from a single source node to all other nodes in a weighted graph. Now, the algorithm processes each node once, updating the shortest node distances as we can see in this illustration here. Now, if we were to delve more into it, the polynomial time complexity of this algorithm, if we were to use a priority queue or a binary heap, is O v plus e log v, where v is the number of vertices and e is the number of edges. Now, v log v is the operations for extracting the minimum distance node from the priority queue, and e log v is operations for updating the distances when traversing edges. Now, this is polynomial time, so it belongs to P. Now, if we were to use an array implemented in Dijkstra's algorithm, then the time complexity would be O v to the power of 2, which is also polynomial. Now, again, the second key point to finding out whether something is polynomial or not is ensuring that it has a deterministic nature. Now, Dijkstra's algorithm is exactly this. It is deterministic. It first selects the vertex with the smallest distance, updates neighbors based on the weights of edges, and it does not rely on any non-deterministic or guessing steps. Again, such as sorting numbers through merge sorts or quick sorts. Dijkstra's algorithm is an algorithm that has instructions from one step to another. It does not rely on any deterministic or guessing steps. After one step, always it is a fixed step. It always has a fixed step right after the first or previous step, ensuring that the deterministic nature happens in the Dijkstra's algorithm, making it a polynomial time. Now, let's go further into discussing what is NP, or non-deterministic polynomial time. So if we were to look at the definition, these are problems where finding a solution is hard, but verifying a given solution is easy, meaning that theoretically, a magical computer could guess the correct answer instantly and check it efficiently. Now, the key points are to an NP to classify whether something is NP or not is that first, no known efficient way to solve these problems on a regular computer, and verification, checking the solution basically, can be done in polynomial time. Now, examples of NP problems are Sudoku, because it's hard to fill the board correctly, but easy to check if a complete board is valid. And also subset sum problems. Say, for example, if we were given a list of numbers, is there a subset that adds up to a specific target? Hard to find the subset, but it is pretty easy to verify a proposed subset. Now, let's delve more deeply into Sudoku and find out why this is NP. So, again, let's define what NP is. NP problems refer to problems where a solution can be verified in polynomial time, but the solution is not necessarily easy to find, but if we were given the solution, it can be checked quickly. So how Sudoku works is that it is basically a puzzle game where the objective is to fill a 9 times 9 grid with numbers, ensuring that every row, column, and 3 times 3 subgrid contains each number from 1 to 9 exactly once, so as you can see here. Now, solving Sudoku by brute force requires trying different combinations of numbers, which grow exponentially in grid size. However, Sudoku is in NP because if you are given a solution, like here, a complete grid, you can easily verify it in polynomial time by checking each row, column, subgrid for correctness. However, again, finding the solution, like going from a incomplete Sudoku board to a complete Sudoku puzzle, it is hard. Finding the solution itself may require checking many possibilities, making it hard to solve efficiently for large or complex problems. Now, Sudoku has been proven to be NP-complete, meaning that it is at least as hard as the hardest problems in NP. And if a polynomial time solution for Sudoku exists, it would mean all NP problems can be solved in polynomial time. Now, that will be it for me. I have explained P and NP, and next we will have some discussions regarding NP Hard and NP Complete by my peers Rindra Adriansyah and Maulana Haq. Thank you.
Okay, moving on. We will be discussing about NP-hard problems. So you may ask, what is an NP-hard problem? Well, the general definition of this problem is that they are problems that are at least as hard as the hardest problems in the problems in NP. Well, in here, we know that trying to solve NP-hard problems would efficiently mean that we can solve all NP problems effectively. We can see an illustration here in the graph on the right, where NP-hard problem basically encapsulates not only NP-complete, but also NP itself. But one thing that we need to note is that NP-hard problems does not mean that they are guaranteed to be NP in that case. So yeah, well, what are the key characteristics then of these types of problems? Well, the first one is that there's no known polynomial time solution for them. As we know and have established that there's no way of solving an NP-hard problem effectively because most of them require exponential time as they grow larger and larger. Next is that at least they are at least as hard as NP problems, where we know that every NP problem can be reduced to an NP-hard problem in polynomial time. Well, to put it simply, if we're able to solve an NP-hard problem, you can solve any NP problem altogether. And lastly, is that these type of problems are included in optimization and decision problems, where they're most commonly seen in scheduling, routing, and optimization tasks. These are very important tasks because they are found in many industries, such as the logistics, AI, and resource management. All right, moving on. Here is one example of an NP-hard problem, which is the traveling salesman problem. Here, we are given the task to determine the shortest possible route that visits each city exactly once. And as simple as it looks like at first, where we only have a very small number of nodes, this problem grows really, really big, really quickly. As we can see here, Each number of routes grows factorially with the number of cities, making it incredibly challenging for larger datasets. And here's also another example of an NP-hard problem, which is the halting problem, where we are given a task to see whether a given program will halt or run indefinitely. This was actually proven by Alan Turing, who was the first proposal of this, is that this problem does not have a general algorithm that can solve it efficiently, making it one of the foundational examples of what an NP-hard problem that is unsolvable altogether. And yeah, that basically concludes what an NP-hard problem is. Moving on, we'll be talking about NP-complete problems with Rindra. Thank you.
Next up, we will be discussing about NP-complete problems and why they are so important. To start, NP-complete problems are a unique class of problems in computational complexity. First of all, they belong to NP. This means that while finding a solution might be hard, verifying a given solution is easy and can be done in polynomial time. Secondly, they are also a part of NP-hard. This means they are at least as difficult as the hardest problems in NP. Here's why they matter. If we find a fast solution to one NP-complete problem, it would mean that every problem in NP could also be solved quickly. Solving these problems efficiently would fundamentally change the way we approach computation. This diagram in the PowerPoint right now shows that NP-complete problems intersect between both NP and NP-hard. They sit at the heart of computational complexity because they connect the hardest solvable problems in NP with the broader challenges of NP-hard problems. Next up, let's focus on an example of an NP-complete problem, the Boolean satisfiability problem, or SAT. Now, SAT asks whether we can assign true or false values to the variables in a Boolean formula so that the entire formula evaluates to true. Now, if such an assignment exists, the formula is called satisfiable, and if it doesn't exist, the formula is unsatisfiable. Like, how is SAT NP complete? The first of all, SAT is an NP. If someone provides a solution, a specific assignment of true or false values, we can quickly verify in polynomial time whether the formula evaluates to true. This makes SAT belong to the NP class. The second one, SAT is NP hard. To prove it, every problem in an NP must be reducible to SAT in polynomial time. This was shown through a process where problems like circuit SAT, which is verifying if a circuit has a satisfying output, input can be translated into SAT formulas. For example, each wire in the circuit is represented as a Boolean variable. Each gate, like AND or NOT, is translated into a set of Boolean constraints, and then the result is a Boolean formula that captures the behavior of the entire circuit. Now, if we can solve the SAT formula efficiently, we can solve the original circuit problem efficiently too. This reducibility proves that SAT is as hard as any problem in NP, earning it the NP hard label. Now, why does SAT matters? SAT was the first problem proven to be NP complete, making it the foundation of this class. It's not just theoretical. SAT solving algorithms are widely used in hardware verification like AI and cryptography. Its status as an NP complete problem makes it as a critical piece of computational complexity. Next up, we will be discussing about how are all of these classes related to each other. We're going to connect everything we've discussed before by examining the relationships between P, NP, NP hard, and NP complete. Here's how these classes are organized. First one is P. These are problems we can solve efficiently in polynomial time. For example, sorting a list or finding the shortest path in a graph. The second one is NP. These are problems where even if finding a solution is hard, verifying a proposed solution is easy. All problems in P are also in NP because if we can solve a problem quickly, we can certainly verify it even quicker. Third one is NP hard. These problems are at least as difficult as the hardest problems in NP. Some NP hard problems are not in NP because their solutions might not even be verifiable in polynomial time. For example, the halting problem is NP hard but not in NP. The final one is NP complete. These are the hardest problems in NP. Why? Because they are both in NP, which means that the solution can be verified efficiently and quickly, and in NP hard, which is as hard as any problem in NP. Now, if we can solve one NP complete problem efficiently, we can unlock solutions for all NP problems. That is all from us from this group presentation. Thank you for listening and thank you for watching. I hope you have a great day.